Well, here we go. Lesson 2-2, compound probabilities. What is this compound business, you ask? Well, compound means more than one. All right, so kind of zooming in here a little bit, we have one probability, and now we have a second probability. So we're looking at two different events here. And how do we find the probability of both of them happening? Now, there might be 3 or 4 or 5 events, who knows, but it definitely will always be more than one in each of your homework problems. How do we calculate these compound probabilities, you ask? Well, very carefully. But much like the fundamental counting principle, we are going to multiply our probabilities together, not add them up. All right, so going back to that little visual here, we are going to multiply probability of x times the probability of y. Now, when you find each probability, you have to kind of be aware of this idea of whether these two events are independent or dependent on each other. And we'll take a look at what each of these words means. Independent events, what are they? They are events where one outcome does not affect the other. Yeah? In other words, one does not know about the other. For example, one coin toss to another coin toss. The next one doesn't know the last one occurred. If you pull out a card from one deck and then you go to another deck and pull another card out, it's not like the one deck knows what the other deck is doing. All right? You could almost say the probability of your attitude in the morning versus somebody else in the class next to you, right? Those probabilities typically don't affect each other. They're independent. But there are other scenarios in life where the attitude or the probability affects one another. All right? So one affects the other outcome. And so, because they know that the second event has occurred, the first event has occurred, then we have to be wary of when we calculate what those probabilities are. Okay? So we got more than one, and we got to know, like, do they know each other? We will still multiply the probabilities together, but you just got to be aware. So here are some examples. Let's say you go to a car dealership. What's the probability of going to a car dealership and then choosing a car to purchase? Are those dependent? And you would say, of course they were, because depending on which dealership you go will determine which cars you can purchase. If you roll a die and then rolling it again, are those two events dependent on each other? And you would say no. What you go to homecoming and, deciding whether to go to homecoming and what you wear on that particular day. Yeah, sure, if you aren't going to homecoming, then you aren't going to dress up. And if you are, why then you would put something special on. Tossing a coin 5 times, right? Here's a compound event, 5 different events. Does the next coin know what the first coin does? And we would say no. All right, so there's a few examples. And let's actually do some calculations now of some of these events. What is the probability, and here's how we're going to write it, of getting a 5 and an ace? And we'll look at this 2 different ways. We'll look at it like with replacement. That means we put the first card back in, and then we'll look at it again with no replacement. All right? So we'll kind of do it twice here so you can see this is a case of not dependency. So this is, I should just say, independent. And this would be a case of dependency. All right, so what's the chances of picking a 5 out of a deck of cards? Well, there's 4 5s out of 52, right? Times, and then we say, again, put the card back in. There are still 52 cards in the deck, and there are 4 aces. So this would be 16 over 2,000 something, but let me check on my calculator here. 52 times 52. 2,704. We could reduce that ratio. I'm not really interested in that. I suppose another way of doing this same problem would be 1/13, because 4/52 reduces to that, and 1/13 would be 1 over 169. So there's a reduced ratio. These two ratios will be identical. I will take either one as an answer, and you can obviously change them both into the same decimal. Now what if you did not replace? Why, there's still 4 out of 52 on the first one, but now the second deck of cards, or sorry, the deck of cards now has one less card in it. Are there still 4 aces in it? Why, sure there are. So the answer would be 16 out of, and this time I would need to make my denominator a little bit smaller, so 2,652. And if I were to convert that into a decimal, just so you know, that's approximately 0.006. See if I move the decimal correctly. Yes. So that's less than 1% of a chance of that occurring. And what about a red card and a black card? Well, how many red cards are there? There's half of them are red and half of them are black. So 1/4 is probably the easiest way to answer it, though you could have done this with the whole deck and said, for example, 26 out of 52 times 26 out of 52. Yeah, and 26 squared and 52 squared we already know, so 676 over 2,704, and that still would give you a 25% chance. Okay? What if you did not replace the cards? Well, the first one is still 26 out of 52, but now the second one, there are still 26 black cards, but there's only 51 cards in the deck. So now we're still going to get 676, but in the denominator we have 2,652. So that's going to be a little bit more than 25%. 2652, checking on my calculator, it's about 25.5%. So if I write it out in a percentage format rounded to the nearest 1/10 of a percent, that's roughly what it would be. Okay. All right, I'm going to leave those for now. We're going to go on and try some other ones. Let's say I've got a situation here where Noah is on the hockey team and he's got 8 different sticks. Okay. And he's planning on going to a game, and 5 of the sticks are wrapped with black tape. So he grabs 2 sticks, doesn't pay attention. He gets there. What is the chances that neither of them are wrapped? Well, what is the chances the first stick was not wrapped? And that would be 3 out of 8, because 5 of them were, so 3 of them were not. Now the second time I grab this, the second stick, there would now be 1 less unwrapped, and there would be only 7 sticks left in the in that bin. So 6 out of 56, which smaller numbers, we should be able to reduce this, dividing them both by 2, we get 3 out of 28. Okay? And looking at a scenario now where they're independent. 12% of the population is left-handed. I don't know if you are. I'm not. I'm right-handed. I'm not part of that 12%. What if we pick 3 people randomly from the world? What is the chances that all 3 would be left-handed? Well, in this case, probability, there's the first person. Why does the second person not change? And why does the third person probability not change? Well, because our population is so large, and they didn't tell us the world population here, but even if they had, these numbers would be so big that it really wouldn't matter that much to the problem. It's still going to stay 12% each time, roughly. So if I take 0.12 to the third power, which is kind of my shortcut, correct? I better do this with a pen, not my disappearing pen, I get 0.001728. So less than 0.1%, right? So 0.2%. Wow, not good chances. Well, what if I pick 10 random people now, but what are the chances that they're all right-handed? Well, if 12% of the people are left-handed, then right-handed would be 88. And where did I get that? Well, if you take 1 minus 0.12, that's going to give me the 88%. And again, I take it to the 10th power because all of these 10 people, again, since it's such a large population, the probabilities aren't going to change from one person to the next person. And so that gives us roughly a 28% chance, okay, that all of them are right-handed. Hopefully that helps you do these problems. And they'll have different types of problems. Sometimes they'll list them out and they'll say, you're grabbing the first 3 pieces. You want them all to be milk duds. So again, you go through the first pile and it's like 10 out of 40. And then the next one would be 1 less. And there's 1 less in the pile. And again, don't forget, we're going to multiply these. And so that's how you do these problems. Hopefully that makes sense. And you can now do the homework problems. Again, we're looking at what we would call, sorry, went too fast there, compound probabilities, more than one. Best of luck as you do your problems.